If you guys have any questions, I'm happy to answer your questions. Yes, sir.
I work a lot in electronics and radio, so I'm very interested in the answer to this question. What kind of gain do you experience out of those receivers and the antennas?
Gain. I'm not sure how to answer that, to be honest with you. We certainly amplify the signals a lot at different stages in the processing.
Do you use supercooling on your antennas?
Yeah, a lot of the detectors are strongly cooled. So, for example, ALMA's detectors will operate at liquid helium temperatures in the cryostat, 4 degrees above absolute zero. Yeah, we cool, I believe, almost all the detectors. Yeah, I'd be happy to try and answer your question about gain. I can talk to the guys over at the Technology Center. The short answer is I'm sure there is, but I don't know enough about that part of the process to answer it accurately. Yes, sir.
For things as big as this kilometer array, has any thought or work been done with phased array antennas that would allow you to build something cheap and flat?
Yes, people are working real hard to build lots of cheap things and make them work together in phased arrays and things like this. There's a lot of really clever ideas being bandied about, and that is certainly one of them. And it's still a push, though, cost-wise.
Is it? Oh.
Yeah. But, ALMA, 10 years ago, people would have said that the ALMA antennas could not be built. Right? They're 12 meters in diameter. They are observing millimeter and submillimeter radiation, so the surface accuracy, right, has to be of order 10 times better than that. And the spec on the surface accuracy is 25 microns RMS from perfect parabola. Yeah.
Well, if it's flat, it'd be a lot easier. You wouldn't have to have all of the aiming and maneuvering.
Yeah, some of the concepts that were in that image I showed you included those kinds of phased arrays. So you could see the flat arrays that were there. I'm trying to think if anybody's... They've started building little demonstrators, is what they call them. So the Australians have put a sizable chunk of money right now into building what they call 10% demonstrators. So they're trying to build something that is 10% of an SKA and demonstrate that it works before expanding out to the full thing. But that is a fundamental issue. What's the detectors? They have to be achievable, and most people target of order $1 billion. People think it's plausible that one could get $1 billion to build this, but implausible that you could get $10 billion. Yeah. Yes, sir.
I'm curious how the arrangement of the arrays actually affects the science you do. I mean, you have more sensitivity and obviously more resolution if it's spaced.
That's right. Primarily, that's right. So the more resolution you want, then the wider you make the array. And so in ALMA's case, the widest separations are 18 kilometers, big distance. As you spread the array out, you lose sensitivity to faint, relatively uniform radio emission in the sky, right? We're pretending we have a much bigger array, but of course we don't, as your question implies, you obviously understand. And that causes you issues. And one of the things that's really important to the NREO right now that we're working hard on is to make radio astronomy more accessible, right? It has a reputation of being hard, right? You got to do a Fourier transform, for heaven's sakes, before you can get an image. And even though astronomers take mathematics and everything, it's very different. And so we have an important initiative within the observatory called end-to-end operations, which is all about making the observatory more accessible so that it appears to someone who's done optical astronomy or someone who's used the Hubble telescope or the Spitzer telescope or the Keck telescope to be more like using those telescopes. So we have pipelines that create the images without the astronomer having to worry about, well, what baselines did I have, and did I flag the bad data, and did the transform work right? I'm trying to make all that easier. But fundamentally, which array you choose, the 0th order selection is resolution, and then sensitivity. And that's true for any interferometer. I'm sorry, somebody had a question. Yes, sir.
The ALMA receivers, what are they made of?
Exotic materials. So for example, and it varies depending on what wavelength. So the lowest frequency ALMA detectors are about 90 gigahertz, and they are a different technology than the terahertz, the very highest frequency. In fact, we don't know how to make the terahertz receiver yet. And the Japanese colleagues have taken on that task. So if you go to Japan and go to Mitaka, which is just outside Tokyo, the astronomers there are, the engineers and the scientists there are working on developing the technologies to efficiently detect radiation in detectors that are robust, that won't break every 12 seconds. Right? They're going to sit at 16,500 feet. So the best thing that I could, let me point you at something and talk a little bit about that for you, because I'm not very good at that part. There are HFETs, which are these silicon technologies, and then there are more exotic materials. So for example, here in Charlottesville, there's a gentleman, Art Lichtenberger, and he runs a lab here on the UVA campus called the Microfabrication Electronics Lab. And he does all this exotic materials development that make it possible. He works with things like niobium, chemical elements, like he makes these wafers that are critical parts of the detectors for the high frequency ALMA.
No, I'm saying, what are the dishes made of?
Oh, excuse me, carbon fiber. Yeah,
And then within?
yeah, 25 microns. Yeah.
And so is there an issue of reflectivity with materials you choose for a radio dish?
Oh, you certainly want to be
everything balanced radio.
Yeah, you certainly want to be efficient. Yeah, and I understand that they're quite efficient. Yeah, yeah. The dishes themselves, other than surface accuracy, aren't a big issue. The hard technology is in detection. Yeah. Thank you very much.